Great pleasure to me to introduce the next speaker of this afternoon, Professor YanYan Lee from Rutgers University. Professor YanYan Lee is a worldwide renowned specialist in the field of fully nonlinear PDEs, conformal geometry, differential geometry. He has, throughout the years, provided many significant contributions to the field. I think he is his first time in IMPA. Today he is going to be talking about symmetry, quantitative Liouville theorems, and analysis of large solutions of conformally invariant, fully nonlinear elliptic equations. YanYan, please.
Thank you, Diego, for the nice, kind introduction. And I also want to thank the organizing committee, in particular Eduardo, and for the kind invitation. It's a great pleasure to be here. As Diego said, first time for me to be at IMPA, so it's really a great pleasure. So, okay, so the talk will be in Euclidean space. We will be doing analysis in the Euclidean space. I will describe very quickly the motivation of our work being described later. So this is we take a compact Riemannian manifold of dimension n greater or equal than 3. And here is the so-called Charlton tensor. This is the Ricci. This is the scalar curvature. And the trace is not 0. So this is not the trace-free Ricci. So when one takes the trace, one gets the scalar curvature. Yeah. So the notation is lambda will be the eigenvalue of this tensor with respect to the metric G. And a fully nonlinear version of the Yamabe problem is like this. So with appropriate gamma, for example, gamma and F. So usually this gamma, we will be taking something like this. So we will take this something like this as gamma. Later I will be more specific. So there's a function f, which is positive here, and say f equal to 0 on the boundary. So suppose that initially the metric, the Charlton tensor, all eigenvalues is in gamma. It's in this part. Then the question is whether or not there exists a conformal metric G tilde, so that for this function f, the curvature with respect to the new metric, conformal metric, is equal to 1. So if one takes gamma to be half plane, this is the gamma. If one take this as on this side is gamma, so actually often denote that as gamma 1. So this will be the boundary of gamma 1. So this is a half space, and then that's exactly the Yamabe problem to solve this. In that case, it can be solved. So then so the answer to that question for a large class of f and gamma would be yes, if one can prove a priori estimates. Namely, assume there are solutions, okay, and then prove that this solution is upper bounded by a constant. So if one can deliver these estimates, and then by previous works for the past maybe 15 years, 10 to 15 years. So then it can be done. So there have been a lot of work devoted to that. So now the question is whether or not one can deliver these estimates. So there are many situations where one already proved such results. I will mention a little bit later. And but for some challenging range, I mean, this is still open. So, okay. So a crucial step is to analyze the behavior of a sequence of blow-up solutions. Namely, suppose we have a sequence of solutions. What happens if this bound is not, does not hold? So what can you say? In general, one would like to end up with a contradiction. So then we proved the upper bound by contradiction argument. So to do that, then one would say that suppose there's a sequence of solutions, the maximum of UK goes to infinity, and we would like to say things about UK. The more you can say, the easier later on you can draw contradiction. So for instance, initially one would say, well, is it possible to prove finitely many blow-up points? So, yeah. So of course, even you know that, it's still very far from getting a contradiction. Yeah. But if you don't know that, it's even further away. So one would like to say that, well, can one say that there is a finite many blow-up points and near each blow-up point? If so, then does UK look like a standard bubble? So, I'll explain later. And namely, one wants to say whether or not you have a very fine asymptotic of this blow-up sequence near an isolated blow-up point. Because if you just say an isolated point of singularity, still anything can happen, one would say. Yeah. So you want to say more. Because if we don't say more, it's harder to continue. Yeah, So here, so in this talk, all the theorems I will be describing will be under these conditions. So these are the conditions. So gamma is an open, convex, symmetric cone vertex at origin, like this. And gamma n is like the first quadrant, where each lambda I is positive. Gamma 1 is half space, like this. That's the one for the Yamabe problem. So F we assume to be C1 in the interior and continues up to the boundary. And F is positive inside, 0 on the boundary. And this is an important condition. So F lambda I, the partial derivative of F in each lambda I direction is positive. So that's the same as ellipticity of the equation being discussed. So we assume ellipticity here. So illuminating examples will be this. So this is the kth elementary symmetric function. So I'm writing it as 1 over k's power. And gamma k is the component where sigma k is positive, and the component contains the positive cone. So that's where gamma k is. Well, it's known that this gamma k will be something like this. It's convex, cone, and so on and so forth. And reaching here, I can just say a few words about earlier, that fully nonlinear version of the Yamabe problem. So for instance, if k is greater or equal than n over 2, okay? So then the existence is known, okay? And actually, a priori estimates is also known. Okay. For k equal to, well, for k equal to 2, it is also known. So existence result is known. A priori estimates are not known. So in that case, the problem is of variational form. There is a functional, okay? There's a variational formulation. So one can prove in that case the minimum is achieved. And for k, well, if the manifold is locally conformally flat, so no matter what, it is known. So the other two cases I mentioned are for general manifolds. So these are essentially the situation now. So what is not known is sigma k, and k is bigger than 2 and less than n over 2. So in this case, in general, there's no variational formulation. So one hope is try to establish a priori estimates. Well, this is one approach we are taking now. So therefore, we try to cover this place. Yeah. So, well, so the talk is about our plan. The project is to get a priori estimates. Yeah. So try to see when we can deliver a priori estimate, because once it's done, the existence follows. So, okay, so let's take m equal to Rn in the setup, or actually, if we rescale a blow-up sequence of solutions of the equation on the manifold, then one will end up with solution of this entire solution, so in Rn. So in that case, this AU will be there. This is an n by n symmetric matrix. This is the Hessian. So everything here is in Rn, Hessian. First derivative. This is an n by n identity matrix. So you take a positive function u, take the AU, look at the eigenvalues, and evaluate it there for your function f. So, well, this AU looks complicated, but actually it is conformally invariant, and actually this is the only one. So there is some characterizing property for this AU. So this is a nitro object. So this equation, in substance, so if you take a Hessian of u instead of this AU, which has Hessian plus certain lower order terms, right? So in that case, and this was done, studied, investigated by Caffarelli, Nirenberg, and Sprague for the Dirichlet problem. So our equation resembles the above. And so what the difference is, somehow AU is not only the Hessian of u, it's the Hessian plus some lower order terms. So, of course, if one add arbitrary lower order terms, it's not expected to have everything going very well. Yeah. So here, there's an additional feature. So this AU is conformally invariant. So there are a lot of symmetries here you would like to exploit. So now I want to describe results in Rn, yeah. So let's recall, this is the condition. So this is in Rn. Gamma is in Rn. It's an open, convex, symmetric cone like this. Vertex at the origin. So it contains the positive cone, contains the first quadrant. It belongs to the half plane where the sum is positive. So it's like this. So we assume ellipticity. That's well, usually in discussing something like this, usually one assumes homogeneity of F and also often assume like concavity of F. So here they are not assumed. So the first theorem is about blow-up analysis. So this is a joint work with Luke Guin. So let's say in Rn, we are on Rn. So in Rn, we have a bore of radius 2. And in B1, the soup goes to infinity. Okay? So we have a sequence of solutions which blows up. So the maximum of UK in the unit bore goes to infinity. And this, we do not assume anything else. There's no assumption on the boundary, etc. So nothing else. So this is the only thing we know. So then the conclusion is for every epsilon positive, one can find a couple of points. So one can find a few points. They are, the distance is bigger than 1 over k. So this is, they are universal, the distance between them is bigger than some universal number. So therefore, one cannot put too many. So there are m points. They are universally distance apart. And this is also, delta is some constant depending on epsilon, but only, yeah, delta. Delta depends on epsilon, yeah. So this is a maximum. At each point, it's a maximum point. So well, and the height are comparable by universal numbers. And the point is near in each universal size bore centered at xi. It is like a so-called standard bubble. So UK is more or less like that. So what is this capital U? Capital U, so capital U is the Sobolev extremum. So this is the Sobolev. And then this is the scaling, yeah, natural scaling. So in particular, this function satisfies minus Laplacian U equal to n minus 2. For instance, yeah, U to the n plus 2 over n minus 2. Okay. So, and also all the other scalings. So when you scale properly, so like this, yeah. So therefore we call them standard bubbles. They come from one single function. Yeah. So UK will be like standard bubbles, modular, small. Yeah. And the next line is the standard bubble will decay as this goes to infinity, as this rate. So the rate I'm writing here is exactly the rate of the standard bubble. So it will go down, okay, like the standard bubble. So this is the description of any sequence of blow-up solutions. Okay. So one may wonder why this function u is just one single function, has nothing to do with f, has nothing to do with gamma. Okay, it's just a universal one. Well, if one take f equal to the sum, and that's the Yamabe equation, and the result I described is due to Rik-Schön. So here, even though for any function f, the asymptotic behavior is still like that, is because of some Liouville theorem with Albin Lee. So it's a result more than 10 years ago. It says that whenever we have there is an entire solution to this, no matter what f is. So one will end up with a solution like that. Okay. So this is something that dictates why we have this bubble. So this result in the case in R4 and f is the second elementary symmetric function. It was first proved by Alice Chang, Gursky, and Paul Yang. So, and in the case, this f is the sum of lambda I. So that's the first elementary symmetric function. And this classification was given by Gidas, Ni, and Nirenberg under some decay assumption. So Caffarelli, Gidas, and Sprague removed the decay assumption, which are very important for applications. So, yeah. So this is the case when f is sigma 1. So that's the. So the blow-up analysis result is closely related to the following theorem. It is a quantitative version of the Liouville theorem mentioned earlier. So for that Liouville theorem, one needs the solution to live in the whole Euclidean space. Here, we want to say, if it lives in a large ball, what can one say? Well, so the statement is like this. So take a solution which is somewhat normalized. One has to have this because those solutions, when you shift away, you can't really say anything. I mean, so this is a very natural normalization condition. Suppose in a ball, u is greater or equal than some fixed constant. In a fixed ball, you look at solution, you want it to be bigger than a fixed constant there. Now, we say that, well, there is a number R bar, so that if solutions live in a large enough ball, then one can say that your solution U will be like a standard solution, modulo epsilon, in a universal constant multiple of R. Delta bar is universal. So of course this implies the Liouville theorem. One can just, because we can control the center and the height. So one will immediately get the Liouville theorem. So this is a quantitative version of the Liouville theorem. So maybe I will, before entering the proof, so how many, I have 1 hour or 50 minutes? 50 minutes. I have 15 minutes. All right. Pardon? You still have 35. I have 35, yeah. So maybe I will describe a result. So in some of these works, to continue also, it is quite important to understand the following equation. So this is gamma. So one needs to understand an equation like this on the boundary of gamma. So this equation, in the case of gamma 1, in this case, so that equation is simply, this is equivalent to harmonic function. Yeah. So for harmonic function, we know everything. But here, when one blows up and so on, one may end up with this equation. So this equation is not elliptic. This is only degenerate elliptic. So for instance, in a paper with Caffarelli and Nirenberg, we had examples showing that for sigma k, the case elementary symmetric function, for k greater or equal than 2, this equation does not have strong maximum principle and does not have Hopf lemma. So this is a degenerate equation. It's not an elliptic. So one would like to understand this equation more, yeah, in order to prove the compactness of solutions to the general Yamabe problem. Well, so maybe I will describe one result. We have a recent result. So this is a result with joint with Luke. And Bo Wang is my student, graduated in May. So we proved something like this. So what we proved is, for example, let's say if one has this equation, so U positive, say U is, say, continuous. So if one has a continuous viscosity solution to this equation, actually one has U is in, let's say, in C Lipschitz of B1. And with estimates. So the gradient is being controlled by U, yeah, upper and lower. So, and I will not describe. So somehow this equation, one needs to try to, it would be good to know more about that equation. Yeah. So now I want to describe the proof of that theorem. So the theorem is about, this is the theorem. So I will only describe this theorem. So I will describe the theorem of the proof. So the proof, so I will assume F is homogeneous. So if it's not homogeneous, some more work is needed. So I would say where one needs to do. So let's not worry about that. So let's say everything is homogeneous. And so here is the proposition. So this proposition says that if we have a sequence of solutions in enlarging balls, so then suppose this Vk will go to a function in C0 norm. So then this V will be classified. It will be classified. They are, in particular, V will be C2. So once it's C2, the earlier Liouville theorem will come in. Even though we are not proving it that way. But anyway, so this is what was needed in the proof. And of course, one may say that this V satisfies the equation in viscosity sense. Well, so naturally, one would say, if we take a V positive, satisfying the equation in Rn in viscosity sense, is that, can one classify that? Well, I believe in that. Yeah, I believe in that. But we cannot deliver that. We don't know how to prove it at this point. So instead, we proved this. So if this V comes from a limit, okay, of a C2 solution, then one can do it. Yeah. So this is something. It would be nice to prove this. Yeah, it's a neat statement. Okay. So the proof of this proposition is like this. And I would like to describe this proof. Somehow there are some ingredients which seem to be useful, maybe in other situations. So this is the limit of Vk. Vk is a sequence of solutions in enlarging balls converging in C0 to this V. Well, V is superharmonic because Vk is. So that comes from the problem. So V is superharmonic. Therefore, it has at infinity a strength like the fundamental solution. And we may assume without loss of generality that Vk minus V is very small, and Vk from below is bigger than that. So this is, one can assume. So then we prove by the method of moving planes or moving spheres as follows. So for every point x in the space, so we have a Vk which converges to V in C0 log, let's say. All right, something like this. So, and so then we make a reflection like that. So we make a reflection. So Vk, we can make x and lambda. So this is the Kelvin transformation. So Kelvin transformation will be like this. So this is the Kelvin transformation. The problem we look at is invariant under conformal transformation. So Vk will satisfy the same equation. So for small lambda, it's very easy to see that for small lambda, this will be below Vk, outside, okay, for small lambda. Okay. So then we define, as usual, lambda k bar is the largest radius, so that this relation is preserved, is hold. So, well, first, this lambda k bar actually has a lower bound, which is independent of k. So that requires an estimate. So the estimate was established before in earlier paper, it reads like this. So you take any f. If this has an upper bound, then the gradient log u is bounded. So it gives Harnack, for instance. Okay, you go to, this is a pure local estimate. If you have a solution upper bounded by b, then we will have gradient log u being controlled. With this control, we will see that lambda k bar will be bounded from below. Okay. So then we have Vk, Kelvin is below Vk itself in a bore of radius lambda k bar. Okay. And this estimate, this local gradient estimate, in the case of kth elementary symmetric function, was established by Guan and Wang in 2003. So now I will let lambda bar to be the lambda k bar limit, the inf, let's say. So lambda k bar is the largest radius for the Kelvin of Vk staying below. So then one can prove by rather standard argument, maximum principle and half lemma, that either it's always infinity or always finite. One doesn't have a mix. So if lambda bar is equal to infinity, then it is elementary to see that V has to be constant. So it's an elementary fact, and this can be ruled out. Our problem doesn't allow that. So now lambda bar has to be finite all the time, and you have this relation. So now the situation is the following. So we have arrived at the following situation. So we have a local Lipschitz positive function, superharmonic, and it has the following property that there is a lambda bar x. For every x, there's a radius. And when you make a Kelvin transformation, the Kelvin transformation is below the function v, okay, outside. Yeah? This means that. And the Kelvin, this function, touches v at infinity. So this simply means this is the value at infinity. Yeah? This is the value of v at infinity. So for every x, there's a bore, finite bore. When we make a Kelvin transformation, the Kelvin transformation stays below v, but gets stuck with v at infinity. Okay, this is the picture. So the question is, what can you do about that? Yeah. Well, the claim is, given the above, one can deduce this v is of this form. Okay. So this implies that. Once we have this, everything is done. Yeah. So that's the main proof. So I would like to describe the proof of this, which I believe can be useful elsewhere. So the proof is based on this lemma. And the main thing is how to apply this lemma. The lemma itself is very elementary. So the main thing is how to use it. So the lemma is for this. So I can draw a function u like this, and I can put a function w1, and I can put another function w2. So in one dimension, so my function now is defined in one dimension. So this function u, and this violates this statement. Yeah. So the function u is not only superharmonic outside the origin, the one I draw is actually harmonic. We have two functions, W1 and W2. They stay below U and touches U at the origin, as I draw. So the conclusion is gradient of W1 should be equal to gradient W2 at the origin, which is certainly not the case in this one-dimensional picture. So the point is, when you go dimension 2 and above, this conclusion holds. So this is exactly how we prove the classification result. So we have a function v. We have a function v which has the following property. You take a point x, there's a radius, okay? And when we make a Kelvin transformation, the Kelvin transformation of v touches from below at infinity of v, okay? So this is, the problem is a conformal invariance. Infinity and the origin is the same. So we have cooked up a lot of functions. So you give me an x, we have a function, okay, and touches the fixed function v at infinity. The fixed function v is superharmonic. So we created a large family of functions, okay, those Kelvin transformations. They have the same gradient at infinity because of this lemma. Okay? They all have the same gradient. So this certainly contains a lot of information. So if one can write out what it tells, so hopefully one gets something. Well, in this case, indeed so. So we just prove it this way. So here we take a Kelvin transformation. Just for convenience, I transform infinity to 0 for simplicity. So this is the Kelvin transformations of V we created. So composed with psi, we call it Wx. So then Wx touches this Kelvin of V at 0. You write like this. And V per psi is superharmonic. So then by the lemma, so here let's take V C1. No? So otherwise you use it on the back point. So by the lemma, all these functions created will have the gradient at 0 equal to a fixed vector V. Okay? So then let's see what it is. Okay? We compute it. We see that the gradient at 0 is equal to this. It's just equal to this. It's equal to that. So namely, the gradient of this function is 0. Namely, this should be a fixed vector. It's a fixed vector. So then it's finished. If you, yeah, this proves the result. So the point is, if we can create a lot of functions which touches a fixed function at the origin, so you can. So 15 minutes. I have 7 minutes. So okay. So now I go to the remaining proof. Yeah. So I will be quick there. So yeah. Okay. So now the remaining proof goes like this. So assume Vk is C2. I look at a normalized situation. So original UK, so I will look at a normalized situation, which is in enlarging bore, we have a solution. And at 0, it's a maximum point, normalized to 1. So we want to handle this first and then to get the others. So this is the main step. So we want to say this Vk and standard bubble differs with an error epsilon u. So first, we say that by local gradient estimates, we mentioned before, Vk will go to a limit along a subsequence, but we have a proposition 1 saying this to identify this V. So we know this Vk will go to U, go to a fixed one. So first lemma is we try to say this Vk is very close to capital U. Okay? So Vk, capital U is infinity is like the fundamental solution. Capital U is something like this. Yeah, this is capital U. So we want to say that Vk is close to that. So we first estimate the minimum of Vk on every sphere is less or equal than 1 plus epsilon. Okay? The minimum is not too far from U. Okay? So the minimum will not be too high. Okay, this is the first estimate. So I will skip the proof. So I prove, yeah. So like okay, I will skip the proof. It's a moving sphere method. So it controls the minimum. So then, so Vk, the minimum is close to that capital U. It's, yeah. So then I prove that Vk is bounded from below by U, essentially. Well, this step is easier because Vk is superharmonic. Okay? Once it's superharmonic, one can estimate from below by harmonic, which we can cook up. Yeah. So this one has. And then we prove that in this very long region, from a fixed R1, where Vk converges to U very, very well, and to there. So the whole integral, we prove it's small. Yeah. So one prove that. Well, I will skip the proof. So once we prove that, we have an energy control. So energy will be small. So Vk in this big annulus region, so the energy is very small. So I still have 4 minutes. So the energy is very small. The energy is very small. And for this equation, because there's a Liouville theorem, the Liouville theorem will say small energy will imply L infinity bound, because the Liouville theorem identified the limit after rescaling, the usual way. So then we know that small energy will give an upper bound. So, and then we can prove that Vk will be upper bounded by U. So this step, Vk is upper bounded by U. So the way to prove it is to rescale. Okay? When we rescale in the annulus region, it's small, and then this Vk tilde will be upper bounded. So it's not that rate, but we have this rate. This rate is enough to give Harnack. So because that rate, we can apply Harnack. So the Harnack, but we already control the minimum along sphere is controlled by U, so the maximum will be controlled. So after that, one needs to rule out oscillations. So now, suppose this Vk does not, maximum goes up. So we know the minimum at most like that. So if the maximum goes to 1 plus 2 epsilon, so that means there is an oscillation on this sphere. So we normalize to the standard one, to the unit sphere. So this oscillation, we put it to the unit sphere. Then this Vk hat will satisfy a degenerate an equation. So it will have a limit. So the limit will be. So we can apply we can apply this local gradient estimate. So there's a Harnack. So one can take limit. So we know before taking limit, there's an oscillation. So after taking limit, the oscillation remains. So the limit is more than C0. So therefore, we end up with a solution which satisfies the degenerate equation in a punctured Euclidean space. But for that one, we an earlier theorem already showed that when we have a solution which is in a punctured Euclidean space, it has to be radial. So, well, but you know this limit has oscillation like this, so it's a contradiction. So after that, so we have proved, yeah, so it's finished then. So then we have settled this normalized situation. So Vk have a maximum at 0, value 1, and so on. So then we want to prove the theorem now. So, well, so with Aubin Li, so we proved that the energy is bounded. So there's a universal energy bound. So once there's a universal energy bound, we can take two universal radius so that in this annulus, less than delta 0. The one for small energy imply L infinity. So then that means we go, there are annulus where UK is actually L infinity controlled. So once you are in that setting, we can, inside this larger ball, take a maximum point, rescale, apply this normalized situation. We are going to take out a unit size ball where you have very good control. In particular, around that point, there's a universal annulus where UK is bounded from above. And then you look at the remaining place, take another maximum point, you will have a universal ball around it under control. This process will finish, and we get the statement of theorem 1. So it's finished.